Well, hello everyone, and welcome to this Data Week Online 2021 session. We are just about to begin, so I'll just take you through some admin before we start. My name is James Thomas, and I'm a data scientist at the Jean Golding Institute at the University of Bristol. Next slide, please, James. So, as I said, welcome. Now, just please be aware this session is being recorded, and that includes anything that you type in the chat as well. Please can everyone make sure that they read through the JGI Code of Conduct and our virtual event policy, which is going to be shared in the chat shortly. And also please make sure that if you are invited to speak, that you just keep your microphone muted unless until it actually comes to your time to speak. Please feel free to introduce yourself in the chat box to the other attendees. We'll be answering questions through the Zoom Q&A facility. So at the bottom of your screen, there will be an icon for chat, but there's also an icon for that says Q&A. If you click on that, that's where you can answer questions of our panelists that we'll get to at the specific times. My colleague Chiara has also shared a link to our short registration form. It's just 2 questions. We'd be really grateful if you could fill that in before the event starts. Next slide, please. So a very quick introduction to the Jean Golding Institute at the University of Bristol. We are the central hub for data science and data intensive research at the university. We're one of 5 research institutes there. And our strategy is to connect multidisciplinary experts across the university and beyond. So we have 4 priority work streams: societal challenges, data visualization, reproducibility and data governance, and fundamental research. And then we have a number of cross-cutting activities where we try and connect these work streams together. One of them being developing communities, which is exactly what we're doing here at the Data Week Online 2021. In addition to this, we offer training, funding, and our Ask JGI help desk service to researchers at or involved with the University of Bristol. And of course, we are involved with the Alan Turing Institute, which is the UK's National Institute for Data Science and Artificial Intelligence. Next slide, please. We have a packed week of events on this week, and this being sort of one of the ones near the start. We have 40 events in total. If you go to our websites, the link is at the bottom of the screen, then you can find our interactive timetable where you can click on any event and book. So I encourage you, if you see anything of interest, I encourage you to do that. Next slide, please, James. So thank you very much to all of our supporters and sponsors. They're all listed here, and without your support, this event wouldn't happen. So thank you very much to all of you. And next slide, please, James. So we encourage you to connect with us during the Data Week by using the hashtag Bristol Data Week on Twitter or mentioning us at JGI Bristol. But you can also follow us on LinkedIn, subscribe to our newsletter on our website, and we also run a blog, and we have many other events and workshops that we run, including our Data Ethics Club, which is run every 2 weeks and includes workshop sessions, which are very interesting and rewarding. So I do encourage you to have a look on our website and find out if there's anything of interest. You should see the links coming up in the chat now. And last slide, please, James. And just to plug our next event, talking of events that we do, if you enjoy Data Week, then I encourage you to find out more about the Jean Golding Institute Showcase, which will be happening in February 2022, next year, at the M Shed in Bristol. So it's a family-friendly event open to the public with lots of speakers, exhibitions, workshops, and the like, and should hopefully be a great event. So we encourage you to look out for that as well. So without further ado, I'd like to hand you over to the host for this session. That is Noel Pringer, who is the Technology Director for Jacobs Clean Energy Limited. They've also been appointed by BEIS to represent the UK at the Senior Industry Advisory Panel of the Gen 4 International Forum. Nawal has 40 years of engineering experience and technology experience in the aerospace, automotive, oil and gas, and nuclear power, and has published over 50 technical publications, including 3 books. So without further ado, over to you, Professor Pringer.
Thank you, James. I would like to add my own welcome to 55 odd participants that we have and my fellow panelists today to discuss this very important and very relevant topic for nuclear industry, for which I worked for nearly last 41 years. So next slide, please. What we are going to be talking about and the next, because you've already had my introduction. Brilliant. So what we are really going to be talking about is use of digital technologies to help nuclear industry, particularly artificial intelligence. And my own experience has been that, yes, we have applied it very successfully, particularly in doing the electron beam welds, checking if those welds have come through okay or not, and what are the reasons why some of those beam welds actually failed the inspection. So it kind of de-risked and accelerated our construction program. And at the same time, also using to speed up the ultrasonic testing of wells. And the third project, which was a marvelous project where it was a Horizon 2020 project, where impact of environment on fatigue and fracture life of steel was being studied. It costs about 15 to 20,000 pounds per assessment per test, and we were able to make AI models which had a free accuracy of about 97%. And the fourth one is predicting material properties for power plant steels. If you knew the chemical composition, the processing, the heat treatment and so on. So we trained AI models to learn from the past data, and then if some parameter is changed or composition is changed, we were able to work out what the tensile properties or the creep properties or the hardness of the material will be. So these are the good things, but what are the challenges? So next slide, please. As you know, and keep pressing the button till it comes to the, yes, there you are. So we all know that as the nuclear power stations have come through the good old generation 1, big dirty reactors, to better generation 2, and nowadays generation 3 or 3 plus, and in near future generation 4, the cost of nuclear power has been going up. And this is the big challenge, because for public confidence, we have to take account of extreme events, and at the same time, the governments, and not just the UK government, our own nuclear sector deal called for 30% reduction in cost in new build. But all around the world, all the governments are asking for reduction in cost, yet at the same time, increase in safety. How are we going to achieve it if we keep on doing engineering the same way as we did before? So this is where new digital technologies, artificial intelligence is going to help us. And my final slide, please. And this is the challenge that we face today. If you look at this familiar curve of expectation versus time, so in the beginning, yes, you trigger innovation, you have inflated expectations, there is a bit of a disillusionment, and then you work things out, a slope of enlightenment and productivity. But if you look at AI, digital technologies like AR, VR, and blockchain, other industry sectors, smartphones, gaming, entertainment, you can see all of them have really way, way ahead. But nuclear, in my opinion, is lagging behind. So at this point, I would like to invite my fellow panelists to share their views. They will have about a couple of minutes each. So to start off with, I would like to invite our first panelist, Professor Paul Wilcox, Professor of Dynamics, Department of Mechanical Engineering, University of Bristol. Over to you, Paul.
Thank you, Noel. Good afternoon, everyone. So as Noel says, I'm Paul Wilcox from the University of Bristol. My area of research is non-destructive evaluation, particularly ultrasonic NDE, but I guess I have some sort of overview of the whole area. I'm also the academic director of the UK Research Centre in NDE, which is a industry academia collaboration that's been running for about almost 20 years now. So the the basic NDE challenge is the inverse problem of turning measurements, which could be done by any number of different modalities. So ultrasound is just one of them. Radiography is another one, turning the measurement into some useful actionable information about the state of a component or plant. And so the challenge from an NDE point of view is the complexity and volume of data that we can acquire is going up and up and up with multi-channel digital systems, automated robotic deployment of NDE devices and permanent monitoring. So we're running into a problem where there's now more data than can be interpreted by humans. So my aspiration would be to take the human out of the loop completely, so we can both deal with the volume of data and also improve the reliability of data analysis by removing human factors, and ultimately extract more information from NDE measurements than is currently possible. So thereby increasing capability, getting data out that is currently beyond the limits of human cognitive ability. So the ideal result would be that at the end of an NDE inspection, rather than having a human in the loop, there would be an output as indicated in the sort of the the diagram on the right, where the AI spits out an answer which not only gives the best guess of what, if there's a defect present, but how confident the system is, what the tolerances are on its assessments. And well, really, why stop there? Why not have that automatically feed into a structural integrity assessment? So this is kind of building towards the digital twin, where it's the NDE measurements in service that close the loop between structural models at manufacturer and the reality of what's actually happening as a plant is operated and ages. The challenges for NDE, I guess, are probably quite common to a lot of different areas where data science is being applied, but particularly one we have is a shortage of genuine, true positive data. So that is components with defects in them, with measurements from them, where the ground truth is known. So really the only way around this is, I think, through high fidelity simulations, but being done at an unprecedented scale. So order of tens of thousands at a minimum before you can start to get any useful findings. There's a big challenge going forward as to how inspections that have some sort of machine learning or AI in the loop can be qualified. So how to get them to convince a regulator that they behave as expected. And like I guess also in most other areas of data science, we need to be able to fully understand exactly what the uncertainty is in our predictions, which is something that is done, I guess, currently with manual data interpretation, but once you start trying to do it algorithmically, it really forces you to confront the problem of exactly what you mean by uncertainty in a systematic and mathematically rigorous way. So that's the challenges from me. I hand over to my next panelist. I'm sorry, I haven't got the agenda, so I don't know who that is.
No, it's okay. Thank you, Paul. Let's move on to our second panelist, which is Dr. Daniel Cogswell. He's from UKRI, Future Leaders Fellow at the University of Sheffield.
Thank you. Yeah, so my background is very much in materials and provision of toughness data for structural integrity assessments and for establishing, I suppose, the manufacturing practices and things like that for large forgings for primary components. So the tact I've taken here is, for me, structural integrity, from my perspective, is about protecting against the extremes of materials variability. So the image in the middle of the slide there is taken from some work that Ed Pickering did for his PhD, in which an ingot was sectioned and then a large number of chemistry measurements were undertaken on that ingot. So you can see there the variability in chemistry that comes with the material. We know what the regions of that ingot are, but we can't necessarily predict where individual features would be present within that ingot. So I just wanted to set that up as really as the kind of an issue there of trying to model and understand that variability. There's lots of different people involved in establishing a robust safety case. So kind of the TAGSI 4 legs are represented by pre-service testing done by the manufacturer, the quality of manufacturer and the suppliers and supplier community doing that, the designer responsible for the assessment, and the end user responsible for forewarning of failure. So the data tends to move around that sort of group in a very particular order and doesn't necessarily get captured very well as it goes through that grouping, often with no feedback loop back to the designer on how to change or improve things. So the hope is, of course, is that digital twins will do that for us, but we're, I think, now probably reaching a point where we understand that we need to start talking to each other and standardizing on wording and terminology around digital twins. And there's also quite a lot of interest in the data formats as well that would do that for us. Paul mentioned uncertainty, huge problem about uncertainty, and how do we carry through those uncertainties through different stages of manufacturing into operation, and how we make use of the actual measurements that we take on components to reinforce that digital twin. So be they manufacturing measurements or in service inspections, does that help us kind of reset the where we are with our knowledge on that component? So for me, the first big challenge is really to standardize our language, even just inside the SI community, about what different things mean, let alone talking to the data community, and trying to frame these things in a way that the data community can hopefully understand and help us. And much like was in the opening slides, you know, we don't want to end up in that trough and disillusioned with what the offering actually is around data science to help us. So thank you very much. I'll pass on to the next person.
Thank you, Dan. Let's just move on to our third panelist, Dr. Elisa Stratulat. She's a technology manager, AI for materials at MyPower Image Analysis. Over to you, Elisa.
Good afternoon, everyone. My name is Elisa Stratulat. I'm a material scientist by background, and I work as a program manager at MyPower Image Analysis. I'm here today to discuss how researchers and engineers can use data and the power of deep learning to innovate. MyPower is a world-leading algorithm development and image analysis software that uses deep learning to extract measurements from complex micrographs. So I'm really coming from the solution area, I think, today. So some of the challenges our customers have are analysis of data, in this case, images, takes a long time. The knowledge from the images they have is really limited. And often the inaccuracy of the results and the high cost of the projects are as well some of their challenges. So with an automated qualitative and quantitative analysis of complex images and microstructures, researchers and engineers can correlate product performance to microstructural characteristics and manufacturing process. This way, is using image analysis and deep learning, our customers stay ahead of the competitors, innovate new materials and products quickly, and increase productivity of the research groups. Thank you.
That's brilliant. Thank you. Let's keep the momentum going and move on to our next panelist, Andy Gattings, Branch Manager for Structural Integrity Branch at EDF, UK NGL. Over to you, Andy. We can see Andy's slide, but can't hear him. Okay, we can come back to Andy. Is Rob ready? We can move on to Rob.
Yeah, can you hear me?
Yes, Rob. Let's just do your slide, please.
Okay.
Come
on. Where's the slide from before that? There it is. They're in the wrong order. Okay, so you'll have to go backwards for the second slide. So I'm Rob Akers. I lead on digital innovation and advanced computing at the UK Atomic Energy Authority, where I've worked for 25 years. And many of you might know from having seen news in the press that we've been set a grand challenge by government to try and put fusion power on the grid in the early 2040s. This really is a moonshot-like endeavour in that we've got to take a giant leap from existing TOCA to up to the reactor regime. And the challenge is, at the moment, we're right at the bottom of the S-curve. So the S-curve, to those who perhaps aren't familiar with it, is a graph of product maturity versus time. And of course, in the modern world, most products sit at the top of the S-curve. So if you're Elon Musk developing rocket engines, you really are working at the top of the S-curve, using design, build, test to try and get an engine design that works. But for fusion, we're nowhere near that level of maturity. So we've got to move up the S-curve incredibly quickly. And the only way we can do that on a 20-year time span is to use huge amounts of data science and high performance computing and try to instantiate our design in silico and absorb new knowledge as it becomes available from machines like ITER, the big 25 billion euro experiment we're building in the south of France, to try and change that design quickly. So we need to build in parametric capability into our digital twin as we move forwards. Now, of course, just being able to code everything up digitally isn't going to be the whole story. It means that as engineers, we need to change the way we do our engineering, or rather, we must re-engineer the engineering process itself. This, of course, anything that involves huge amounts of people is going to be a grand challenge in its own right. The good news, though, is that we're not alone. Those people at Airbus and British Aerospace and Rolls-Royce are trying to work out how to build hybrid electric jet turbines and aircraft, and they face the same challenge. How do you design these products and get them certified in silico? Now, I thought I'd quickly just put up the next slide, which I think is the slide before, because they're the wrong way around, just by way of an advert. We're not alone in nuclear. You can see all of these different fields on this slide that's been put together by the Brunel Challenge bid team. This is a consortium of industry players in the big engineering world who want to deliver net zero innovation. So you've got Team Tempest there, who are the next generation fighter systems, and you've got the ZEAL project looking at net zero autonomous logistics, offshore wind, etc. Many of these programs government funded. I'd like to posit the argument that the challenges we're facing lie in common across these engineering sectors. So it makes sense for UK to work together as a community. And that's exactly what Brunel Challenge is around. It's around multi and interdisciplinary research and innovation, and the idea that a problem shared is a problem halved. So aerospace and nuclear working together. And I think that's probably beyond my 2 minutes, so I'll leave it there.
Thank you. Good point there, Rob. If Andy is still not there, we can move on to us.
It's okay. Can you hear me, Mr. Chair?
Oh, Andy, you're there. Well done. Let's get going.
This is what happens when you have a mechanical engineer with IT. I do apologise.
No, it's okay. He's a branch manager for structural integrity branch at EDF. Over to you, Andy.
Yeah, thank you, Mr. Chair. So I'm responsible for the provision of structural integrity technical support to the 8 UK operating nuclear assets, 7 AGRs and one PWR sizable B. On the slide there, I've got to put, sorry, apologies for not putting any whizzy diagrams up. It is what it is, but essentially, you know, this is all about the provision of safety cases that demonstrate how we manage risk alarp. You know, nuclear safety is our overriding priority, and you can appreciate that the key foundation of that is demonstration of integrity. And that is relevant to pipe work pressure vessels, pumps, valves, reactor internals. And if you think about the nature of the operating environment, as I said there, the materials, the complexity of loading, and how much we're pushing our designs in terms of extended lifetimes, we have some very challenging problems to solve. And that necessitates having a well-developed and suitably sharp set of tools and procedures. And that covers all aspects of the structural integrity bandwidth. So all from, you know, confirming state of plant, so making sure that we have good tools, processes, techniques available for volumetric surface inspection, remote operations, through to sentencing what we find, materials understanding, making best use of our materials data sets, and then all the way through then to structural analysis, where you put all of those component parts together and you seek to demonstrate margins for your key components. and then you need good procedures to assess floor tolerance, in-service degradation. All of those component parts, you know, continual innovation and improvement is a must, because standing still is not an option. So one of the things I am very keen and I promote within my branch and my business is that outward facing collaboration with academia and across industry, because there's a lot of good practice out there that we should be benchmarking, working in support of UK PLC. And that's not just about seeing our existing assets through to end of generation. That's also about new build, supporting our new build aspirations. And also, if you look further ahead, advanced modular reactors. And there's an interesting one there insofar as the 40, 50 years of high temperature knowledge and experience that we have accumulated from predecessor companies and all the way back to CGB, all around the AGR support. That is very relevant and useful. And we need to protect that in terms of AMR development going forward. And so if you think about the AGRs, over the next 10 years, they will all go to get their end of generation. We need to protect that resource, protect that knowledge, that experience for the benefit of not just the business, but the wider UK PLC. So these activities, the discussions today are a key part of that engagement, that benchmarking, and the continual drive to always look for how we can further develop our tools and techniques to support safe and reliable operation and meet those UK targets on emissions. And that's it from me, Mr. Chair.
Thank you, Andy. And let's go to our final panelist, Dr. Simon Lewis. Simon?
I'm Simon Lewis, and officially speaking, I am the operations manager for Norton Straw Consultancy. We're a small engineering consultancy specialising in engineering simulation and numerical modelling of real-world systems. So my background is very much in structural integrity. PhD at Bristol many years ago in fracture mechanics. I spent a large part of my career doing analysis and life estimation and supporting safety cases for people like EDF and those other industries. But really my interest in a lot of the discussions that I'm having here today is how we model, how we make predictions for engineering systems. And I think there's a huge amount of potential in a lot of the things that have been discussed. But certainly my experience is that often big data is not really something that necessarily exists as we would want it to for a lot of engineering infrastructure. So, you know, we might want a big truckload of data. What we usually end up with is, you know, either a small box or very little. And so we're often in the position of, well, how do we make use of all of these emerging tools when we don't have lots of data? And I think for me, it's combining all the knowledge that we've built up over the years, all the physical systems understanding that we already have, combining that with some of the emerging techniques around kind of statistics, data analysis, machine learning methods, and using all of that together so we can make the best use of what we have. So I think my angle here is really looking to hang on to all of the physics-based understanding that we have and use it to increase the power of the data that we have available. And vice versa, you know, using the increasing availability of data to then improve the quality, the speed, the efficiency of a lot of the physics-based predictions that we're doing, and ultimately to make simulation and underpinning safety cases quicker and cheaper for everyone involved.
Lovely. Thank you so much, Simon. This point that you've made from the mechanistic understanding we get from physics, moving over to the data-centric machine learning and that connection that you're trying to make, very important point. Let's, with thanks to all the 6 fellow panelists, let's just move on for about 15-20 minutes of discussion. I had a quick look at the Q&A and I did not see any questions there. So whilst you are taking time to type your questions, I'm really pleased, and I'm going to open this for discussion among ourselves, to notice several good opportunities that have been highlighted, but at the same time, some challenges, like we had earlier on from Paul about the need to qualify an AI system because nuclear is highly regulated. Also, we had the same point being made later by Daniel and others about the uncertainty, and then standardizing the terminology, you know, some kind of harmonization. If it is going to be our industry practice to use AI, then we need to have some kind of a common terminology, common standard, and so on. And a very good point made by Rob and others is, you know, the outward facing collaboration with other academics or people from the other sectors. So it isn't nuclear sector on our own, but we need to learn from others. So a good, several opportunities, and I've noted about 4 or 5 very, you know, positive points which have come out where we need to work together. But at this point I open, oh, there is one question. Let me just have a quick look at it. Oh yes, Norman Swindles from Faraday Limited. Hello, Norman. So he's been working on ISO 10303. This is engineering properties and materials information. And this is to help develop civil nuclear supply chain. Standard can represent data from NDE tests for 3 methods. Technology provides common. So this is more of a comment. Yes, I'm familiar with this work, Norman. I think you had spoken at the Nuclear Institute about it. So why is it proving very difficult for nuclear sector to take advantage of 30 years of global and development of this technology? Okay, so what he's saying is there is an ISO standard out there. So why is it that's taking us that long to catch up with this experience? So I mean, I have an answer to this, but any of my fellow panelists would come in, would like to come in?
I think perhaps it's a symptom of what I see as a slightly wider problem, in that I think there's the old adage that when you have a hammer, everything looks like a nail. And I think across engineering in particular, I think there's quite a habit of people have the tools and methods that they're familiar with and they like, and they're very focused on using that tool for everything. So, you know, you see lots of people desperate to use CFD for everything, or AI for everything, or, you know, NDT, or whatever their area is. I think there's a bit of a habit that perhaps we all often get very focused on the tool set and the methods, rather than taking a step back and sort of saying, well, what is the solution that we are seeking to get to, and what are the best tools for that solution? And I think I think, you know, that's true for all of us a little bit. And yeah, I think perhaps not adopting things like existing standards is perhaps a bit of a temptation to reinvent the wheel, because we all think we can do better ourselves, when actually we'd be perhaps better doing more of this, more collaborative working, more sharing of information.
Yeah.
So there's all a lot of time and effort.
Yeah, thank you, Simon. I mean, the point is that there is a standard out there for data exchange, but it is not just the data exchange we are talking about here. We are talking about analyzing that data, or learning from the data using AI. So that's the major issue that we have. Any other contribution, questions?
I could perhaps just add a few words on top
yes,
of that.
Rob.
And yeah, so I think in the engineering world, there's a lack of interoperability across sectors. And I think it's largely driven by the fact that there are 4 big product lifecycle management vendors that tend to be used, and they tend to try to lock down the technology so that you have to use all of their tools. But of course, as soon as you try to do any product design that requires supply chains, very complex supply chains, it means that you've got to then exchange data and information to organizations who are using different systems to you, because they've bought into a different line of products. So those lack of standards are almost baked into the business models of a lot of the tool providers at the moment. And for us, the only solution really is to try and move as much open source as we possibly can. So the lack of standards and the lack of interoperability is going to cripple us moving forwards unless we do something about it.
Sure, Rob. And we have a suggestion from Lion Evans, who has suggested that why not use OpenBIM?
Yeah.
So that's just a suggestion from.
So OpenBIM definitely, but I mean the PLM providers are supposed to use OpenPLM as standards. But you know, there's more to it than that. It's obviously very complex, but just getting everybody to play nicely with the idea that we want interoperability, I think is absolutely key. The challenge is there are organisations that make money out of not being interoperable.
I think it's only getting to it. I think the key for me here is, I think the two things I've been to the table. Firstly, I think there's a cultural thing. So within an organisation, you have to have the right culture. It's all too easy to just do what you've always done. So you need to lead from the top and encourage people to go out and engage and look for those harmonies, those areas to to do things to a common standard. I think the other thing I'm starting to see a bit more of now, I think there is a growing acceptance that the pool of resource and expertise within the UK is quite limited, and therefore it's to everyone's benefit to collaborate, to work together. So I think some of those old behaviours I saw when I first joined the business, some mid-90s, I do sense that it's changing quite significantly, especially over the last few days, where we're starting to get partnerships, collaborative working for new reactor design to properly help UK PLC. So I do think it's starting to improve, but I do think a lot of this is then within each organisation, you have to have the right culture.
Agree more.
Thank you. We got two very interesting questions also. First one I'll go with is Lee Marget from Manchester. Is saying that there is misunderstanding regarding the difference between uncertainty and dealing with uncertainty. And I would like to invite Professor Paul Wilcox to give a response to this, because uncertainty quantification and structural integrity is an issue here.
Thank you for inviting me. I'm not sure I'm particularly well qualified to answer on the bigger picture of structural integrity, but I mean, certainly the way that NDE is going, it's and this is kind of independent of the data side. It's all about not just providing a single number. It's about providing ideally some sort of probability distribution of what is believed to be the state of a component that could then feed into the next level of structural integrity assessment. So that's not exactly my area at all as to how the uncertainty propagates through, but I know that's an area that other people do specialize in. But then, of course, that means we have to understand what the uncertainty is in our measurements. There's some obvious things like the effects of noise, which are fairly easy to model, but then the epistemic uncertainty associated with, well, especially if we're using, say, machine learning to interpret measurements, well, how much uncertainty was there in the models that we used to train the machine learning networks on, and how do we actually go about quantifying that? So this, I mean, these are open research topics as far as I'm concerned in the NDE field at the moment. I probably shouldn't say any more before I dig myself into a hole, but maybe someone who understands better about this could pick up the baton at that
Paul,
point.
I totally agree with you. Data-centric approach will only help you if you have the data. But I think the issue here when we are talking about uncertainty is the unknown unknowns. If there is no data, you don't even know what type of data, then how do you know what you do not know? So I agree with you. And I also agree with Lee that there is a difference between uncertainty and dealing with uncertainty. But, okay.
Can I just come in on that?
Sure.
Yeah, we've traditionally kept ourselves safe by very, very large safety factors involved in all of these designs. And as our methods have got better and better, and we're looking at potentially, more and more granularity on these things, we may be predicting, say, larger stresses involved in terms of peaks and things like that. So there's a trade-off there between, like you say, the unknown unknowns, which are now becoming kind of known unknowns, or hopefully known knowns as well, that at some point we have to give up those safety factors or change them in some way. And it's going to be someone who's very brave to eventually make that jump. And generating the evidence for that, I think, is really, really difficult. So,
okay, sorry, Simon, carry on.
I think it is beginning to happen. I've seen some evidence of it in nuclear already, but I know EDF have some experience with probabilistic safety cases, and things like Monte Carlo assessments for damage calculations that have been used to underpin safety cases, and certainly in other areas, gas turbines is one that immediately springs to mind, where in some businesses, not all of them, but in some certainly, this use of sort of much more probabilistic approaches to life estimation, underpinning safety cases, all that sort of stuff is becoming more and more standard. It's not everywhere yet, and I think it kind of comes back to that sort of sharing of information piece, that there's a feel perhaps in some areas that it's too hard, it's too complicated, it's somehow trying to pull a fast one on the regulators when you can't calculate the life that you'd like normally. And I think that impression still persists in some areas, but I think I'll put out there are people out there who have experience of doing this, and we could be better making.
Thank you, Simon. I would like to bring in now Dr. Elisa to answer this next question, which is to do with image analysis. So Bronwyn Edge from Sellafield Limited has asked if you've got any case studies of AI imaging being used within active areas to help aid waste categorization. I mean, we all know that high resolution images are very difficult to get in radiation areas because radiation can brown out the lenses and so on. So Elisa, any help?
Yes, thank you. Thank you so much for the question. Yes, there are a few applications on our website, so it might not be nuclear necessarily related, but it will give you an idea of what you can do with image analysis. And I think, yes, we do need good images when it comes to image analysis, but the difference between modern technologies nowadays and more traditional segmentation methods is that we can deal with images that are less perfect. So when I say that modern segmentation can use deep learning to train the computer into dealing with poorer images. So I hope that answered the question to some extent.
Okay, and I think we are running out of time. There are a couple of questions asking about the case studies. I'm pretty sure that there will be some kind of a website set up. I'm just hoping that JGI will make that provision, and we all can share our various case studies. And another thought from Nicholas that nuclear safety regulation in UK is non-prescriptive. Yes, we all know that it's all based on safety cases. So one of the jobs is to convince the regulator to take AI-based evaluations into account. Good. I think we can close our discussion session now. We have just 5 minutes left. And what I would like to do, first of all, is to thank all the participants, all the people who actually listened and asked the questions, and all the panelists for sharing their views. As I said earlier on, several good opportunities have been identified, particularly on using AI to predict material behaviors or even come up with new materials, structural integrity, and to help remove uncertainty. And I must say, we didn't talk about it, but also to use the natural language processing, cognitive search capability to help write the nuclear safety cases for the UK regulator, because it is a non-prescriptive regulator who bases their assessment on the arguments and evidence, which we can use the AI to help formulate. So these were good opportunities, but at the same time, we can summarize by saying that there is still work to be done. Anything that we produce needs to be qualified. Yes, we need to still do some more work on how we deal with uncertainty and how we quantify uncertainty. And we all must come together to also agree on standardized terminology, have harmonized approach in applying this new technology to help us. and collaboration. I think Rob's made a good point that nuclear sector is not on its own. There are other industry sectors who are facing similar problems. Maybe they are a little bit more advanced than us, but we can learn from them. So with that, I would like to thank everyone, particularly James from JGI for helping us to organize it, and the Southwest Nuclear Hub. Okay.